Hello and welcome, everyone. My name is Dane Menke. I am the Digital Marketing Manager here at REGENESIS and Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we don't address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's presentation will focus on challenges of PFAS in groundwater and lessons learned from Michigan's survey of community water. With that, I'd like to introduce our presenters for today. We are pleased to have with us Steve Sliver of Michigan Department of Environmental Quality. Steve Sliver has 32 years of state government experience and is the Executive Director of the Michigan PFAS Action Response Team, or MPART. He was assigned to MPART in April of 2018, where he served as Michigan DEQ's senior representative within the organization. In that role, Steve Sliver led several major MPART initiatives, including the recently completed sampling of public water systems throughout the state for PFAS. We are also pleased to have with us today Patricia Byrnes Lyman, Investigation and Remediation Manager at Michigan Department of Military Veterans Affairs. Patricia Byrnes Lyman has over 25 years experience in the environmental industry and has worked as an environmental engineer for multiple large international environmental consulting firms, contributing technical input on commercial, military, and industrial facility projects throughout New England and Michigan. In her position with the Michigan Department of Military Veterans Affairs, she is the PFAS lead and manages environmental investigation and remediation efforts across the state at Michigan Army National Guard facilities. We are also pleased to have with us today Ryan Moore, Great Lakes District Manager at REGENESIS. Ryan Moore has 18 years of experience as an environmental project manager and laboratory account executive relating to multimedia contamination sites throughout the U.S. His experience is focused on site investigations of soil and groundwater contamination, corrective action evaluations, operation and maintenance of remediation systems, large soil removal remedial projects, in situ groundwater and soil treatment, vapor intrusion assessments, and environmental laboratory operations such as QA/QC evaluations, data interpretations, and business development. All right, that concludes our introduction. So now I will hand things over to Steve Sliver to get us started.
Okay, thank you, Dane. Appreciate the opportunity here. Good afternoon, everybody. We'll start out with just a little bit of background on the compounds we're talking about. Many of you already know a lot about these, but the per and polyfluoroalkyl substances, or PFAS for short. These compounds enjoy one of the strongest bonds in chemistry, the carbon-fluorine bond. They act as surfactants. They are hydrophobic and oleophobic, which means they don't like water or oil. They act as surfactants like detergents, wetting agents, emulsifiers, foaming agents, and dispersants. We began developing these back in the 1940s, and there's over 5,000 of them today. So I want to start out as well with some common PFAS abbreviations because we're all guilty of overgeneralizing, and when we talk about PFAS, we're really only talking about a few of them that we have much in. The first two here you see PFOA, PFOS. Those are ones that nowadays are not as much in the marketplace. They stopped making those and using them, and we now are dealing with replacement compounds. But the PFOA that was used in Teflon, for example, PFOS in Scotchgard. And some of the other ones you see here are others that we have more information on. We typically are looking right now for 14 or 24 of these compounds within that suite of 5,000. So it's often easier to talk about what PFAS may not be used in than it is to do an inventory of everything that they are. But everything from foams used for firefighting, mist suppressants for chrome plating baths, Teflon coatings on pans, stain resistant and water repellent coatings for fabrics, even things like dental floss and the Rain-X that we put on our windshields to help the water bead. So why are we concerned about these? Well, they're rather ubiquitous given all of the uses of them, and they're persistent. That strong carbon-fluorine bond means they don't break down naturally very well out in the environment. And we understand that some of these, perhaps more than others, have a tendency to bioaccumulate, build up in our tissues and the tissues of other animals, fish, for example. And they've been associated with adverse health effects. But equally as important is we don't have all of the information we would like to have about their impacts on people and the environment, and we really don't have what we would call a complete regulatory structure for them yet. I'd like to show this slide here. This conceptual site model really shows the challenges we have in dealing with PFAS, because essentially we are cycling them through the ecosystem. Since they don't break down well and we're not effectively destroying them, we're essentially cycling them through. And a good example, if you see in the middle of the page here, is a landfill. Many of the consumer products are ultimately end up in a landfill. And some of the PFAS compounds may leach out of them and end up in the landfill leachate, which could go to a wastewater treatment plant, which may not be able to effectively remove all the PFAS compounds as much as we'd like, so they end up in the surface water. And then they could end up bioaccumulating in the fish or going back into a drinking water supply or elsewhere into the ecosystem. So in Michigan, back in 2017, recognizing that the emerging nature or concern with these contaminants, we decided to establish a multi-agency approach, which is rather unique within the nation. And this M part is the acronym we use for Michigan's PFAS Action and Response Team. It's comprised of representatives from multiple agencies within state government that are charged with protecting the environment, natural resources, overseeing agriculture, public health, even military and veterans affairs facilities, and airports, and fire marshal. And essentially this team provides a multi-agency cooperative approach for all that we do in addressing PFAS throughout the state. Primary responsibility of this team is protecting public health, but when you're dealing with an emerging contaminant, you also have to start at the beginning, everything from how do we actually standardize our sampling and analytical to what do we do ultimately to prevent future contamination. So I want to focus the rest of my time on what Michigan has done to evaluate drinking water. So in addition to investigating contamination at known or suspected sites of contamination and looking at what might be occurring in the surface waters and the discharges to those, we wanted to have a proactive approach to identify what the occurrence of PFAS are in Michigan's drinking water supply and then do what's necessary to reduce those exposures. And so last year we decided to sample all community water supplies within the state, and then all schools and licensed daycares that had their own wells. That sampling effort was completed in December, and the results from that effort will also be used to inform what we do next as far as additional sampling. So this is over 1,700 supplies. Michigan has another 9,000 non-community supply wells, plus over 1 million private residential wells that may not ever be evaluated as part of an active site investigation. So we'll use these results to help inform where we go next with those. So here's the results, and overall we can say the state of the drinking water in Michigan is rather good. 90% of the supplies that we tested were non-detect for PFAS. That means less than 2 parts per trillion of the reporting limit. And this evaluation was done using the EPA method 537. That's the one the US EPA recognizes for testing drinking water, 14 contaminants. And 7% of the supplies had a concentration between non-detect and 10 parts per trillion total PFAS. And that 10 part per trillion is a number that our consultants and our MPART team agreed that if you stay below that for total PFAS, that's a sum of all those 14 compounds, that you're likely are not dealing with a source of contamination that needs to be addressed today. We had another 3%, which we call supplies within that middle bucket, about 62 supplies that had something more than that 10, but less than the 70 parts per trillion action level. And those require some additional follow-up, and we only had a couple, which I'll talk about as well, that were over that 70 part per trillion lifetime health advisory level, which Michigan has recognized. So the 10 to 70, that middle bucket, Michigan is now going to go forward and provide quarterly monitoring for the supplies that had something more than 10 and less than 70 PFOA, PFOS in any combination. We'll do quarterly monitoring of those to verify whether the concentrations are varying over time. We'll also work with them to make sure that customers are notified and if there are ways they can minimize exposure, and also consider whether or not there are alternative water sources or treatments that they should be evaluating should the need arise. And so this quarterly monitoring that we'll be doing over the next 12 months will cover the water supplies for 500,000 Michigan residents. So the very small group of folks that may have more than 70 parts per trillion, that's an immediate response, and we'll talk a little bit about here, where it's more than notify your residents, it's get them on alternate water right away, and then address, if it's a municipal supply, what alternatives we have going forward. Also consider evaluating where that release is coming from and how to remediate it. And I'll mention now the one. We had 2 supplies that had concentrations over the 70 parts per trillion. One is a school in an isolated area of the state, and we are still evaluating that one. That had only about 100 parts per trillion PFOS. We're not sure what the source is, so we are actively investigating that. And the students and teachers, approximately 300 people, are on bottled water as we pursue that investigation. But the one that most of you probably are familiar with is the city of Parchment, Michigan, which is a supply serving over 3,100 residents in Parchment and Cooper Township. That back at the end of July last year, we found concentrations of PFOA and PFOS 20 times the lifetime health advisory level. And that required an immediate response. I share this timeline here just to give you an idea of how quickly things transpired from the time that we actually got the result in one afternoon to the residents being on bottled water the next morning, and then after a series of transitioning to a new supply and verifying that that supply was acceptable from a number of drinking water quality parameters, they were on that new supply within a month. So let's talk a little bit here about what the municipal supply did. And this is the first example of what we're aware in the country where we have totally shocked a system overnight and replaced the source water. They went from having 3 production wells one day to the next day being connected via fire hydrants temporarily to a adjacent municipal supply from the city of Kalamazoo. And any of you involved in the drinking water program can well imagine, the potential impacts and the concerns that you would have to ensure that you've addressed all the water quality parameters going forward. So when you have contamination of supply wells for a municipal water supply, that also should trigger, as it did in the city of Parchment, an investigation of what impacts there might be on private residential wells. And as you can see from this diagram here, the three polygons, the blue polygons up in the middle left of the page, those are the supply wells for the city of Parchment. And one of the concerns or challenges we have had in Michigan as we investigate sources of contamination impacted water supplies is how do we be strategic in trying to determine who else might be impacted and have an understanding of what the results might mean when we start doing testing around potential sources of contamination. So in this case, what you can see is the light blue shaded area. That is actually a mile radius around the wells that were impacted. And then that purple shaded area is the wellhead protection area for those wells. And so the first choice, not that it was going to be the end of all sampling, was to let's first focus within that wellhead protection area a mile out. And that's where we began sampling. And what's also important to recognize is when you get results, what is your public health action plan going to be? That's the second major component when we're doing these investigations. When you get a result, what do you do with that result? And so here, again, being strategic in your sampling, knowing where the groundwater flow direction is coming from and whether you do or don't have a high strength source to deal with, do you put the residents on presumptive remedies or bottled water depending on that result going forward. And so this is where Department of Environmental Quality and Department of Public Health have been working very closely together to make sure that we have a very clear plan going forward so that we are, number one, investigating the folks that need to be investigated and putting them on the remedies as rapidly as possible. We also are concerned about the source. Once we've made sure that we've identified and reduced exposures in the municipal supply and any private residential wells in the area, is focusing on the source. And so you can see from this diagram here, there were numerous possible sources that might be influencing the groundwater quality for that municipal system. And so the DEQ's role, working closely with the local officials, is to do file reviews, identify potential sources in the area, evaluate our hydrogeologic studies. What do we or don't we know about groundwater flow direction and the different aquifers in the area? What sort of monitoring do we have, and can we do some additional monitoring around these potential sources? And then who are the responsible parties? And this is probably a really good opportunity to point out that in many cases we're finding throughout the state where we have essentially remediated what we thought were the contaminants in groundwater aquifers. And maybe decades ago we had sampled for and put in installed mitigation and remediation systems and thought we were done. What we are finding now as we go back to these potential sources of contamination is that PFAS have been behaving very differently in groundwater and soil. A lot of the models that we have to predict the plumes and characterize the contamination haven't been working so well, whether we're not applying them correctly or the models themselves need to be improved. And that was definitely the case here as we see going forward potential sources where we had been monitoring and not noticing contaminants getting off site. Talk a little bit about the keys to success in Parchment. And first and foremost, as you remember the timeline, it was a rapid succession of events triggered by a sample result. And we would not have been so successful as a community or state if it had not been for the residents in the city of Parchment and Cooper Township and their adjacent community of Kalamazoo working together to resolve things quickly. And I believe as well as the structure that we set up with MPART had been key to a rapid succession of getting solutions implemented in that community, because we already had state agencies who were very well aware of what PFAS is and what we needed to do to address the contamination. And as well, as you can see, this is just a picture here of a community town hall where we had 800 people. And what made that town hall, I think, very successful has been the actual presentations to all the residents from state local, and federal officials all having a single plan which explained what we knew and what we didn't know and what our proposal was going forward for doing the investigations, and being very transparent with the citizens, routinely communicating with them, because there were a lot of things that we didn't know. And so we went from actually having hourly to daily to weekly updates with the residents, which we believe was very effective at keeping everybody on the same page and moving forward. One thing that came out of this, which I think many communities can take advantage of as well, is that we kind of wrote the playbook on how to address not only PFAS, but emerging contaminants that may come out of left field in a sampling event. And we actually have available now on our website a template for PFAS readiness plans, where we're encouraging communities with their own municipal supply to identify up front, okay, who would be involved if an event like this happened? What resources do we have? How would we even distribute bottled water? Do we have bottled water available to us? How quickly can we get it? And then not forget that there are helpful regulatory programs, especially the drinking water program, where we have engineers and scientists who can assist communities as they explore ways to fix their system and provide the drinking water to the community. And just a few other quick takeaways here. We didn't spend a lot of time on it, but specialized sampling and analytical. We are looking for contaminants that people have not looked for historically in the past, and at very small levels, in the part per trillion level. And that means that there's not a lot of labs out there that can do this testing, and even the sampling protocols not only need to be established but followed carefully. When Michigan did some of the testing, and especially when Parchment happened, and we started trying to expedite samples at labs across the country, we were hearing from other states that the labs were backing up because of the burden Michigan was putting on them. And so typically today, given the capacity that we have at labs across the country, we're still looking at 3 to 4 weeks many times for getting a result. So that's something to understand can be an ongoing challenge. Also, as I mentioned earlier, the challenges of source identification and characterization. The PFAS contaminants are showing up in places where we wouldn't necessarily expect them to be, and in areas where we thought we had cleaned them up or cleaned up other contaminants in the past. And again, some of the challenges, more studies are needed on how to better predict the environmental transport and fate of these contaminants throughout the ecosystem. And one thing we didn't touch a whole lot on, but we are testing for at least 14 PFAS contaminants. We have recommendations based upon EPA's lifetime health advisory for 2 of them. But you can imagine when other PFAS show up in those analyses that questions arise. And this is where our Department of Health and Human Services folks really come into play to help communities and local health officials understand whether there might be any other public health response necessary to address some of these other contaminants where we don't have a lot of information available. And lastly, again, just to emphasize the important point of preparedness, now that we've been through this once, we've learned some things, and communities can develop their own preparedness plans based upon what we've learned. And here, just to highlight as well, we've got a lot of information out on the web, including results from our public water supply testing, and even, as you'll hear here shortly, about some of the sites, including Camp Grayling. We have a lot of information on the web that might be helpful to you. So what I'm going to do now is transition and hand this off to Ryan and Patti. So thank you, everybody.
Yeah, thank you, Steve. This is Ryan Moore, the Great Lakes District Manager for REGENESIS. I'm joined here with Patti Lyman. Just advance. There we go. Again, I'm joined here with Patti Lyman with the Michigan Veterans Affairs, Military and Veterans Affairs Office. We're going to talk about a site in northern Michigan up in Grayling Army Airfield, which is part of the Camp Grayling Joint Maneuver Training Center. Patti, could you just maybe give us a little bit of a background of the site and some of the challenges you've faced with groundwater remediation there?
Sure, Ryan, I'd like to do that. So Camp Grayling has a very long history. It's been in operation for over 100 years. It's a very large area. It's actually the largest National Guard training center in the country. It's used for training for military staff, emergency responders, private sector, individuals from all over the world, and it's also the home of the Grayling Army Airfield. So the area that we are doing our pilot study in is an area of a former bulk storage fuel facility. It was 3 above ground storage tanks that were used for containing diesel fuel. And that's in the southwest corner of the Grayling Army Airfield. Generally, the area is flat, slopes down south to the south. Superficial geology is glacial outwash, sands and gravels, very permeable soils. There's a non-continuous clay layer at about 25 to 27 feet, and a second clay layer in some areas that occurs at 45 to 60 feet below ground surface. Groundwater is around 17 feet, varies a little bit, but not too much. And groundwater flows to the south toward the Saab River. It's got a complex release history since it has such a long history of use. There's been diesel fuel releases, there's TCE and PCE releases that were associated with the cleaning of artillery vehicles, and there's PFAS has been released as a result of some fire training in the area. Most of these releases, we actually don't know the dates and the precise locations that they took place. Because of the complex number of releases and different compounds, there's a complex remediation history. We started in 1984 addressing the diesel plume. The treatment technologies have changed over time. Once we established there was PCE in the groundwater also, we changed the treatment technology. Then we established the locations of some precise PCE source areas, so we instituted some changes resolved in that. And then 2016, as a result of some DoD concern about PFAS being at military facilities, we sampled some of the existing groundwater wells in the bulk storage area, and we got some detects of PFAS in those monitoring wells. In the following year, in 2017, we did some vertical aquifer profiling along the fence line in this area, and we did come up with some detects of PFAS along the fence line border there. In 2018, we've initiated this pilot study of the plume stop in the former bulk storage area, and the intention of this pilot study is to polish the PCE plume that remains, and also to investigate the effectiveness of the plume stop to address the PFAS in the groundwater.
Yeah, thank you, Patti. You know, just as a little bit of a background on plume stop, many of you guys who are attending the webinar have either had plume stop applied at your site, or you've looked at or evaluated it. So I'm not going to get into a lot of the history of plume stop, but I want to kind of get some of the basics of it. You know, it's colloidal activated carbon, and what that means is it's activated carbon particles milled down to very small size and scale, 1 to 2 microns, which is the size of red blood cells. So it's very, very small. It's suspended in a water polymer solution that helps with distribution widely at low pressure traditional direct push methods or application methods. You know, no high pressures or fracking required to apply plume stop. It acts extremely fast on the absorption side. It's because of the huge surface area of the activated carbon particles. In essence, what we're trying to do is convert the polluted aquifer into a purifying filter. Some of the goals when plume stop was developed was to treat the contaminant flux zones and to control back diffusion of contaminants from more low permeable zones. In this slide, kind of what you see here is the plume stop being applied through the sand, getting uniform coverage. Below it's the clay that would act as the source of future back diffusion. And then even up above the treatment zone can act as a future source of contamination. So again, we're trying to treat that flux zone and prevent contaminants from moving on down gradient. So back to Grayling Army Airfield. Again, here's an aerial of the facility. We're operating down in the southwest corner of the former bulk storage tank location. So when Patty and I started setting this up, what we wanted to do is to test kind of a simple plume cutoff area. And in this diagram here, it's a series of injection points where we apply plume stop through the vertical treatment. And then as contaminated groundwater passes through, we're actually containing those contaminants and purifying the water. And so what's being discharged on the down gradient side of the treatment line is clean groundwater. And so this was kind of the concept of the test. And here's a diagram, more of a little engineering kind of diagram. You see we had a series of 9 injection points that are the orange diamonds. It's about 45 feet across, I believe. Kind of did a little of a semi-arc application approach. This is just to account for any potential variation, groundwater flow direction. The blue triangles, those are the existing, or the monitoring wells. So you got 2 upgradient, MW29A, that's screened from 15 to 20 feet. MW29B that's screened 21 to 26 feet. These are 5-foot intervals, kind of keeping in accordance with the DEQ's requirements on monitoring at the site. In the center of the screen, we've got 2 additional triangles. One's a blue, one's kind of a green colored. Those are about 6 feet of the injection line. And then on the far bottom side of the slide, we have 2 additional monitoring wells, so kind of about 16 feet away from the injection line to test, how far down gradient we're going to see the results. You'll also notice here there are several square boxes. Some of them are black and some of them are kind of this yellow-orange color. These are our searcher core locations where we actually advance the geoprobe macro core, hold a core sample, and then try to visually say, can we see plume stop? And so we're going to kind of focus in on the SB8 area in the corner, right side. On the picture on the left, that's the core from SB8. The top right-hand corner of that picture is 0 feet, and the bottom left-hand corner is the 30 feet. As you see, the black from the third core from the right is actually where about 15 feet where you start seeing the plume stop show up visually. And then it continues all the way down to around that 26, 27 feet mark where you start seeing the clay. What we also do, and we're not only just visually looking at it in the core sample, but we'll take a piece of soil and we'll add it to vials with water, usually every 1 or 2 foot interval, and we'll do kind of a shake test. And that's what the picture on the right shows is when we take that soil sample, add it to the water, shake it, and kind of get a little separation and say, how much plume stop is really showing up? Is it showing up on the interval that we are looking to treat? And as you can see, from 17 to 27 feet, we've got pretty good, pretty uniform coverage of the plume stop. The vial that's labeled 15 feet, that's actually Vado's soil. So it was not in the groundwater, but what it does show is that, we're not applying the plume stop above our target treatment interval. To kind of look at this again and back to like what plume stop is designed for, again, we're treating the contaminant flux zone that's shown here, getting very good uniform coverage. We're preventing back diffusion from that clay on a future day as it starts to come back out from it, or preventing additional leaching from above the treatment interval. So let's get into the results a little bit. It's just a graph. We have about 132 days of post-application data. On the x-axis, we have the number of days post-application, and then on the y-axis, we have the contaminant concentrations, and in this case, total PFAS on a nanogram per liter scale. Plume stop was applied at day 0. And then the first 2 sets of data points I'm providing here are the upgradient monitoring well locations, so MW29A and MW29B. As you see, it's relatively flat, little variation in MW29A, but overall pretty consistent contaminants concentrations. The next 2 sets of data that I'm providing are the near down gradient monitoring well locations, MW29 and MW29C. Both of these are 6 feet down gradient of the injection line. And as you see, the first sampling event, which was about 1 month post-application, we had non-detect. And it's been non-detect for the PFAS contaminants throughout the duration of performance monitoring. And then MW29E, that is about 16 feet down gradient, had a similar response as the 2 near down gradient monitoring well locations. And then we have MW29D. It looks a little different, and that's because we do not actually have a sample from the 1 month post-application event. When they went out to sample it, it was observed that a little bit of plume stop was in that well. So the decision was made to not sample it until it cleared up naturally on its own, which it did before the 2 month post-application event. When we did sample it, as you see, it went down to non-detect and has been non-detect ever since. So we did mention this was a commingled plume, so I definitely want to talk about the PCE results as well. Again, the x-axis is the days post-application, and the y-axis is the contaminant concentration, and in this case, PCE and micrograms per liter scale. Plume stop, again, was applied at day 0. And just like before, I'm going to show the first 2 monitoring wells are for the upgrading locations. Again, very consistent, pretty flat, not many changes in the contaminant concentrations fluxing into the plume stop treatment line. MW29 and 29C, which are 6 feet downgradient, again, 1 month post-application, removed all PCE, dissolved phase PCE from the groundwater and has been non-detect ever since the first month. MW29E, this was 16 feet, had a very significant reduction, didn't quite go to non-detect, but a very nice dose response. But as you see, at the 2 month post-application, around 60 days, it did go to non-detect, and then it's maintained non-detect ever since. And then just like before on the PFAS results, the PCE sample was not collected from MW29D at the 1 month post-application, but when we did collect a sample, it was at non-detect and has been non-detect ever since. So just kind of quick in summary, what this shows me is that, plume stop is a proven technology across the country for a lot of contaminants, but this specific study is kind of showing that we can eliminate risk of PFAS in groundwater. It's a passive plume management strategy. I mean, what I mean by that is we're not having any infrastructure that we have to leave in place from like a large scale pump and treat system. There's no long-term monitoring or no going out, once a week to check a system. We put it in, we're done. It's easily implemented in the field. We can mobilize to many locations that could be very difficult to scale up a physical mechanical system. With plume stop and the way we apply it through direct push, typically, we can maneuver a lot of areas that other remediation mechanisms may not be as ideal. When compared to pump and treat, it can be very cost effective. Again, you don't have any of this long-term maintenance or weekly visits to a site to address this. And it will last for decades. I know we didn't get into some of the isotherm data now on plume stop related to PFAS, but we've done several technical bulletins, previous webinars that we've had that we'll get into this. And 2, we can provide some journal articles that are being completed by third parties that are peer reviewed and scientifically published that kind of gets into the longevity of plume stop related to PFAS. So if you're interested in that, we can definitely provide that after the webinar here. So kind of next steps, some of the things we're trying to expand upon the field test right now. Some additional monitoring wells are going in this week. Some side gradient, some up gradient wells, some additional down gradient wells, trying to get a better handle of the specific groundwater flow in that region and that specific kind of bulk storage area. And then there'll be future sampling events as well. Patti, do you want to kind of maybe talk with us a little bit about your activities moving forward on the remedial investigation and kind of strategies you guys are looking at?
Sure. So we're early on in the investigations at the airfield and at Camp Grayling in general. As I mentioned, we only discovered PFAS there a little over 2 years ago now. And so at the airfield, we've completed the field work for the SI investigation, but that's being conducted by the National Guard for the DoD, and they're haven't finished the report yet, so I'm not privy to the results of that investigation as of yet, but we're fairly certain we're going to move on to a remedial investigation at the airfield, and but that's still in the planning stages.
Yeah, thank you. So with that, I think we're at our question time period.
All right, thank you very much, Ryan. That does conclude the formal section of our presentation, and at this point we are ready to shift into the question and answer portion of the webcast. Before we do this, just a few reminders. First, you'll receive a follow-up email with a brief survey. We really appreciate your feedback, so please take a minute to let us know how we did. Also, after the webinar, you'll receive a link to the recording as soon as it is available. All right, so let's circle back to the questions. Let's see here. First question, this is for Steve, and the question is, what is MPART doing to evaluate treatment options for drinking water and waste streams?
Okay, thanks for that question. So we're doing a couple of things. Within MPART, we have a work group comprised of representatives of our departments of environmental quality and health and human services and others that act as a clearinghouse to both inventory and evaluate various treatment and remediation technologies. And so, in addition to that, we also are working with a professor out of one of Michigan's universities to help us evaluate different technologies and identify where more research might be needed. We know that many view the options as limited today to things like granular activated carbon, reverse osmosis, and or ionized resins. And we might be very limited on the destruction technologies. So another thing that we are doing as well is we are getting ready to establish a roundtable of various representatives from waste disposal industry, manufacturers, and academia to determine what the technologies are out there today and where we believe we need more research and who can actually help fill the gaps of where the research is needed.
Okay, thanks, Steve. Next question, also another one for Steve, and the question is Michigan pursuing an MCL for drinking water and PFAS levels?
Okay, so at this time, we are not formally pursuing a standard for drinking water, but with that said, as we talked about earlier, Michigan has been, as we've essentially adopted the Lifetime Health Advisory recommendation issued by EPA for PFOS and PFOA, any combination of those at 70 parts per trillion. And I guess more important than that is all of the work that we've done so far, both in investigating and remediating or mitigating any of the contamination. We've been able to do that without actually having an enforceable standard under the drinking water program. We have in Michigan an enforceable standard for groundwater protection of drinking water at 70 parts per trillion for those two compounds, as well as we have enforceable standards in our surface water program of, for example, PFOS at 11 parts per trillion of a discharge into any surface waters, any wastewater effluents. And we're using those standards to both identify and reduce any of the concentrations we're finding out there in the environment while we are considering what sort of standards we might need in the drinking water program.
Okay, thank you very much. So here is another question for you, Steve, and that question is, what are you doing about contamination in surface water across the state?
Okay, and I just alluded to that a little bit. So in Michigan, we have enforceable standards for both PFOS and PFOA in surface water. And so a couple of things that we've done in Michigan, we've been doing for the past several years. Number one, we've integrated the analysis of the PFAS compounds into our ambient water testing, where we go around the state on a routine basis and analyze waters in various watersheds for a number of different contaminants. And we're using that to determine, number one, are there any concentrations out there outside of what someone might consider a man-made background, which, by the way, in Michigan, we believe is probably closer to the non-detected 2 part per trillion range. And if we are in an area and through this ambient water testing find something higher, for example, like 40 or 50, that then triggers an evaluation within the watershed looking upstream on what some of those potential sources might be. We also have asked all of our wastewater treatment plants, the public-owned treatment works, and their industrial pre-treatment programs to look upstream at their industrial users to screen them for whether or not they might have PFAS in their discharge. And if they do, to require them to test, and if they find it, to look at ways to reduce the amount of contaminants coming into the headworks of the wastewater treatment plant. In general, just to reduce further any inputs of PFAS contaminants into the waterways in the state.
All right. Let's see here. Next question is for Patti. Patti, the question is, what are the future remediation plans at Camp Grayling?
That's an excellent question. Right now, we're in the very early stages of the investigation. As I said, it's going through the CERCLA process through DOD and the National Guard Bureau. So we really can't make any long-term plans until we determine magnitude and extent, which we're in the process of doing now. So our future actions are going to be determined by what we find in the next year or so in the field work.
Okay, thanks, Patti. Next question here is for Ryan. Ryan, the question is, what states have approved the use of plume stop on sites?
Yeah, good question. Plume stop has been around for 4 or 5 years now. It's widely accepted across the U.S. It's been applied and throughout here in the Midwest, and I'm located, Michigan, Ohio, Indiana, Wisconsin, Illinois. So it's pretty widely accepted. I don't know of any states who have not approved it. Typically, state agencies want to have a little bit of discussion about what's in it, how does it work. But other than that, it's pretty widely accepted.
Okay, thanks, Ryan. Here, back to Steve. Here's another question for Steve. The question is, was the sampling from your community survey, was that sampling from finished water or raw water?
So it depends on the supply. So all of I believe we have 75 systems that have surface water intakes. So in those systems, we did a sample of the intake and of the finished water. And generally all systems with finished water were tested for that as well.
Okay, great. So here is another question for you, Steve, and the question is, did you take into consideration the types of wells and construction materials into the results? And they give it as an example, some wells have Teflon tubing, for example.
So basically our focus has been on what the consumers of the water supply were exposed to. And so you're right that there could be some potential contamination there, and I think more at the residential level if there were ways to screen out those sorts of influences. But when it came to the municipal water supply, we were testing the finished water regardless of what the components were of the system. So the results all are of the finished water that is being distributed out to the residents.
Okay, thank you, Steve. Let's see here. Next question is for Ryan. And the question is, with plume stop, what happens to the PFAS that is captured in situ? Does it stay captured for perpetuity?
Yeah, good question. So activated carbon is kind of a dynamic system, and so there's always some coming off and some coming back on or being absorbed onto the carbon. We talk about like what's the longevity of it. This gets into a lot of our isotherm studies that we've conducted, and in most cases where the PFAS contaminant levels down in the part per trillion range, we're going to be able to hold on to that those compounds for decades. And some of the studies are upwards of 50, 60, 70 years. It's always going to have a little bit of movement in there, and that's just the nature of the PFAS until we get a destructive mechanism in place. Eventually, if you're just doing a treatment line or treatment barrier, eventually it will fill up and would release contaminants. The question again is how long, and in most cases we're going to be able to lock this up for decades to allow for time for remedial investigations, looking at other ways to provide water, etc. Good question.
Okay, thanks, Ryan. Here's another question related to plume stop, and that is, Does plume stop work with other contaminants? And as examples, they give non-organics and metals.
Yeah, good question. Traditionally, we're using plume stop with the organics, so fluorinated solvents, lower levels of benzene, PFAS, PCBs, anything that can be absorbed by activated carbon could definitely be utilized for treatment plume stop. Some of the metals do have some affinity to activated carbon. It would be a case-by-case basis. A lot of times it's based upon the species of the metal. We'd want to work with our R&D department to see if it's applicable to specific metal that you would be, or specific inorganic that you're trying to target. So, in general rule though, if it has affinity, the compound has affinity to activated carbon, then there's probably some applicability of plume stop.
Okay, thank you. Here's another plume stop related question, Ryan, and that's, do you have success in fractured bedrock environments?
Yeah, absolutely. I mean, like I said, plume stop's been widely accepted, so it's been applied on a variety of types of sites, including fractured bedrock. I've worked on a couple sites, up in Wisconsin and some other locations where they had, some fractured sandstones, and we've applied plume stop, and it's been absolutely great for those settings. In general, if you can inject water, you can inject plume stop. It's very similar consistencies. And so it's just a matter of the delivery and understanding with a fractured bedrock, understanding those fractures. Where are they at? Where do they go? What are they connected to? Which anyone who's working on fractured bedrock sites understand the difficulty of that characterization. But there is applicability with plume stop in fractured bedrock.
Okay, thanks, Ryan. Let's see here. Next question. This one is for Patti, and it is, has there been any coordination with federal agencies or feedback from them regarding anything from the sampling methods or analytical methods used or for remediation success and or challenges?
Okay, are you talking, okay. So in terms of the plume stop pilot study, we discussed it with the DEQ, our local state agency, and they gave us a consensus to go forward with it. We also, part of the funding for the plume stop pilot came from the National Guard Bureau, so they're completely aware of the process and provided some funding to focus primarily on the PCE portion of the plume, but it involved the installation of the plume stop. Because in terms of the general investigation at the site, right now the site is being investigated by the National Guard Bureau and through the CERCLA process. So we're using a slightly different parameters in our analysis, at least in the first phase in the site inspection process. We're not using the same parameter list that the state uses. We're using the EPA and DOD list of PFAS parameters.
Okay, thanks, Patti. Let's see here. Next question is, it's probably mainly directed to Ryan, although also perhaps Patti. The question is, what did the vertical, it's regarding the Camp Grayling case study, what did the vertical profiling show in relation to the migration of PFAS?
Yeah, good question. On this site, we were not able to do some of the more higher res flux studies that we would maybe do on some other plume stop sites. But what we did find is that when we did our vertical profiling was relatively uniform sand from that, where groundwater started at around 17 feet down to the clay, which was, again, right around 26, 27. There was a little coarsening in some of the areas, but overall it was relatively uniform. And then we had the kind of a clay confining layer in the area we were at. So a lot of plume stop sites or plume stop projects, and so someone who's asking this question might be more familiar with some of these other sites where we'll actually put in some passive flux meters and try to get an idea of contaminant flux or groundwater velocities within a more narrow range, say, every 5 feet or every 2 or 3 feet. On this site, we weren't able to do that. We were kind of limited in some of the, we had some limitations on being able to employ some of those higher res characterization. Good question, though.
Okay, thanks, Ryan. Let's see. Next question is another question for you, Ryan. It is in a commingled plume situation, do you find plume stop remaining effective for similar durations between the different contaminants? And they give as an example PCE and PFAS.
Yeah, a great example. I believe, and I'd have to look at some of the isotherm data to confirm this, but I believe, the PFAS has a little bit higher affinity towards the activated carbon. Like PFOS, for example, would have higher affinity than I think the PCE does. A lot of it, the most thing that matters the most are the starting concentrations and then the groundwater velocities. And so what's that mass flux coming through the area? So if for this situation, if the PCE was an order of magnitude higher than the roughly 10 parts per billion that we were applying at, say, then it could have a less effectiveness on the PCE and actually start breaking through if we didn't adjust the carbon content or the plume stop content. So it can be just as longevity with the organics as with the PFAS. One of the things I want to point out is that with PCE or like petroleum hydrocarbons, there's destructive mechanisms that we can co-apply with the plume stop. For example, we can add our micro ZBI with the plume stop for the PCE and address that contaminant. So then it's no longer exhibiting demand on the plume stop system, so it can focus in kind of, so to speak, on that PFAS.
Okay, thanks, Ryan. Let's see, this question might be for Steve, and it is, what testing methods would you recommend to demonstrate the potential efficacy of plume stop given a site's unique groundwater flow and geological conditions?
Yeah, I can take this. When we're talking about testing for plume stop, sites, we're looking at a lot of factors. And so, we may look at like total organic carbon. We're going to look at non-target compounds. So if it's a petroleum situation, you're not just looking at a benzene, you want to look at TPH. If it's commingled with, heavier compounds such as the PAHs or naphthalene, we want to look at that. So we want to look at everything that could exhibit a demand on the activated carbon, not just the specific compounds we may be targeting. Again, we also want to evaluate what the aquifer is doing. So we want to look at geochemistry, sulfate, some of the iron, ORP, pH temperature. So we want to get an idea if it's a compound that we can biodegrade. Do we want to go that approach? What conditions the aquifer to start with? What do we got to do to get it optimized for biodegradation? If it's just PFAS related, again, we want to identify, is this commingled? Are there other VOCs? Fire training areas potentially have a lot of commingled stuff there, because what do? They add a bunch of fuel, they light it on fire, and then they try to put it out with these firefighting foams. And so it's naturally going to have, benzenes or TPH, something in there that's going to exhibit demand. Those compounds may not move as far from the area like PFAS, but they still will exhibit a demand. So, good question.
Okay, thanks, Ryan. Let's see here. Here's another question. This one is for Patti, and the question is, did PFAS contamination at Camp Grayling demonstrate any distribution trends? And the example that they say is laterally or vertically, independent of groundwater flow direction.
Of the data I've seen, no. It's generally following groundwater flow direction quite precisely. And as I said, we have recently finished the initial subsurface investigation on the airfield, and I don't have the detailed results back. The final report on that won't be published probably until mid to late summer. So I don't really have enough data to make a knowledgeable statement about that.
Okay, thanks, Patti. Let's see here. Next question. It looks like we're just about approaching our out of time, but perhaps time for at least one more. This question is for Ryan, and it is plume stop effective on higher initial concentrations of PCE? What is the upper limit?
Yeah, I mean, a lot of it just kind of depends on what are your site goals, and where are your receptors at in relationship to these high concentrations. You know, plume stop is very effective when used in combination with other mechanisms. And so if you've got maybe a Dean apple situation, that maybe plume stop's not appropriate in that specific zone, it might be more appropriate to be downgrading a little bit, and then maybe combine that with a chemical oxidation approach or mechanical system approach or excavation for that higher concentrations, and then you kind of utilize plume stop where it fits nicely. So I don't want to get into like just trying to say put a number on it, because it's used a lot of places. You know, if your reduction is only at 50% gold, then it obviously can be used at a higher concentration than if your reduction is 3 orders of magnitude, right? So if that was your goal. So depends on the site, depends on the setting. You know, there's a lot of factors, so it's hard to put like a specific number. But yeah, you know, it's things that we can at REGENESIS we can take a look at for people and help them with the evaluation process, and look at the site information and try to understand your goals, and just try to see if it's appropriate or not for your site.
All right, thank you so much. We are out of time, so that's going to be the end of our chat questions. So if we did not get to your question, someone will make an effort to follow up with you. If you'd like to learn more about remediation solutions from REGENESIS, please visit regenesis.com. Thanks again very much to our presenters, Steve Sliver, Patricia Byrnes Lyman, and Ryan Moore. And thanks to everyone who could join us. Have a great day.